Today we're going to talk about two things, but the goal is really just one, which is to use the fundamental theorem of line integrals to actually integrate some of these work integrals that we've been looking at. In particular, one specific kind, and those are for conservative vector fields. Okay, so let's just kind of review a little bit. So far, we've talked about work integrals, where we can find the work performed by a vector field when it moves a particle from one point to the other. And that calculation was the line integral of f dot dr. Or we also attributed it to f dot t ds. Kind of the accumulated effect of the tangent vectors. Let's see, what else did we talk about? We also split up the work integral as little f of xy dx plus little g of xy dy. Okay, so we actually took the dot product of the vector field with dx and dy. And remember that this is still all for the same vector field. So all these mean the same thing. And that's kind of what we've been working on, evaluating. Lots of different ways to do it. Okay, now what we're going to focus on today first is independence of path. And the idea here is we're interested in, let's say we have a vector field. Maybe it looks something like this. And let's say we want to move, bless you, along a fixed path from the origin, we'll call that P, to another point over here, let's call it Q. Bless you. Okay, the idea here is that and we'll just kind of do the shortened version because I do want to get this one done in one day. If the vector field is conservative, meaning that the vector field is the gradient of some other function, some potential function, then the work does not depend on the path. So suppose that this blue vector field here was a conservative one, okay? Then really I could take any path that I wanted to get from P to Q. I could go this way. I could go straight from P to Q. I could do one of these. It really doesn't matter. The idea is that as long as we're going from P to Q, the work done by the vector field and moving that particle is going to be independent of path. So it won't matter how we get from one point to the other. And that's only for conservative vector fields. Okay? Now, with that being said, we have the fundamental theorem of line integrals. So the conditions are, let's see, first we're going to suppose, morning, suppose that the vector field f of xy is the usual little f, little g, And suppose that this vector field is conservative. If the vector field f of x, y is the gradient of some potential function, which is what it means for it to be conservative, and if C is any piecewise smooth curve starting at, let's say, the point x naught, y naught, and ending at x1, y1, then the fundamental theorem of line integrals says that we can evaluate the work done, which is the line integral of f dot dr, by simply using this potential function up here and using that as kind of like the antiderivative, and we would evaluate the endpoints and initial points just like we would for a normal integral. So we would just calculate phi of x1, y1 minus phi of x naught, y naught. So whenever we have a conservative vector field, if we can find, which we will work on today, the potential function, we don't have to parameterize the path and do all that stuff that we did in 15.2. Okay? Or turn everything in terms of just one variable. All right? Now, the proof for this, because I don't want to give you any homework over winter break, I'm going to skip. Because I want to make sure I get this done today. It's in the book if you're interested. It's not a hard proof. Basically, what you need to know so far, if the vector field is conservative, how we get from one point to the other doesn't matter. And if we have that condition met, then to evaluate the line integral, we can just do this calculation here. Obviously, we're going to work on how we find this. Because if we don't have this potential function, we have to find it in order to do this. Okay, so for an example, let's just start off easy where maybe we know a lot of information. So let's confirm that the vector field f of x, y equals 2xy I plus x squared minus y j is conservative with potential function x squared y minus 1/2 y squared. Then go ahead and evaluate the line integral of f dot dr for the path C, where the path C goes from the point -1, 4 to the point 1, 2. So again, -1, 4 starting, ending at 1, 2. Okay, so again, we're starting easy. They're telling us everything we need to know. We just need to show that it actually works. How do we know if the vector field is conservative? So the gradient of the potential function has to be equal to the vector field. So if we take the gradient of x squared y minus 1/2 y squared, what is partial x going to be? And partial y would be? Which is equal to f. Okay, so f is conservative. And now that we've established that, we don't care what curve this is. It could be any curve, really. As long as we're starting at -1, 4 and ending at 1, 2, then we will evaluate the line integral of f dot dr along that path by simply evaluating the potential function at x1, y1. In other words, endpoint, and subtracting the potential function evaluated at our initial point. So we're going to do phi of 1, 2 minus phi of -1, 4, which is going to be, let's see, plug in 2 and 1, that becomes 2 minus 1/2 y squared, it'll be 2. And now evaluated at -1, 4. X squared y will be 1 times 4, so 4 minus 1/2 of 16, so 8. So here we're going to get 4. Any questions so far? It's a lot quieter without Roma here, huh? Okay. Before we go there, let's do this. Line integrals along closed paths. So here we're talking about a scenario where we start at x naught, y naught, and maybe we come back around and we end up right back where we started. Hey, it's on my desk. Just going to say that's a little late for Roma. At this point, he's probably not coming. Okay. So if we have a closed path, okay, then the following all mean the same thing. So f of xy equals vector field little f of xy. G of xy is conservative. Means the same thing, and you guys can probably figure this out on your own. If we have a closed path, and we're talking about conservative vector fields here, what's this line integral going to be equal to?
0.
Good. And of course, if this is conservative, then the line integral of f dot dr is independent of path. from any point P to any point Q. And again, the usual conditions, smooth curves, yada, yada, yada. So all three of these mean the same thing. In other words, if you've established somehow that you took the line integral of a vector field from one point to another, and you did 2 or 3 different paths, got the same answer, now we're thinking maybe it's a conservative vector field. If you find the line integral for a closed path, and you get 0, we know that it's a conservative vector field. If we have a conservative vector field, then both of the other things have to necessarily be true. Okay? So, let me add this, if closed. Okay, so just make sure that you really understand the notion here. It's pretty simple stuff. Okay? Now, some terminology. And as far as talking about paths, okay, we say something like this is a simple path. Something like this it's not simple. So if it intersects itself, now we're no longer talking about a simple path. Okay? Simply connected looks something like this. We have a closed path, doesn't intersect itself, and then there's this little domain or region that's within that closed path. And then we have multiply connected. We still have that same scenario, closed path, but now we have some holes in here. So that D is pretty much the same as for the simply connected region, but now we have something missing. Okay, so this, since we're talking about closed paths, is a good time to introduce this idea when we start talking about Green's theorem tomorrow. This will come back and help us do that. Okay. Yes?
Is multiply, do those holes have a path too?
It won't matter, but yeah.
Like how did you trace that from one point to here?
Well, as we're going to talk about tomorrow, in order for us to get from here to here, like if we're going to trace the whole region, I mean, we can play ahead a little bit. You're going to have to, at some point, go here, right? So you're going to have to connect from here to here, trace this, and then do what? Come back. So essentially this path that we just went forward and back on will cancel out. Because if this is a conservative vector field, right, if you go from here to here and then from here back to where we start, it's going to end up being 0 for that part. And then you can do the same thing here. So eventually you'll trace everything you need to trace, but getting to that location inside, path won't matter because it'll end up dropping out.
So the particle can move inside of the
Mm-hmm.
thing with the simply
So maybe we have two different, yeah. You could have one thing going out here and then another particle here, so then you do have cumulative work for 1, 2, 3 paths possible. Or if we have one particle that, let's say it's going all the way around, goes to that little point inside, does a little lap, come back, same thing here. I mean, connecting from the path on the outside to the path on the inside, that will be irrelevant if it's a conservative vector field.
So for the simply connected, it particle like moves inside of the thing too.
For the simply connected, it just goes around.
Doesn't move inside.
No.
For
Yes.
For the not simple, just for the terminally ones, not the ones that terminate on the end.
Uh-huh.
Could you say that there's like a simply connected thing within it, and if we like only looked at one part of it, and then could we make it like into a multiply connected type thing?
So something like this.
Yeah.
And
So it is like rounded, like it's
Yeah, I mean, you'd have to split it up. That's pretty much what you would do, is think of it into 3 different sections where you have this path, then a closed path here, and then this path here, which is actually interesting because if it's a conservative vector field, when we go from here to here,
and it's like
do we have to do this?
no.
No. Does that make sense? Because that's going to drop out. So really all that matters is from here to here. In fact, if this is a conservative vector field, even if we're doing this goofy path, could we just make our own path to get from here to here? We could, right? Because it doesn't matter how we get there. Yes?
If that not simple one like went back around to connect to the original point, would that be multiply connected?
So like this?
Right.
Yes.
Yeah.
It would be. Yes.
For simply connected, it will always be 0.
Yes. If it's a conservative vector field.
We'll deal with more words now.
Yes. Yes.
So is the one you just drew on the not simple is that multiply connected?
Yes.
Okay.
It just happens to be that the whole or the region now is connected to it's tangent to the outer curve. Good questions. Anything else? Wow, that was cool. Usually when I go through this, everybody's like, okay, let's move on. You guys are all like, ooh, let's talk about these regions. Okay, that's good. All right, so if you recall a couple days ago, I said, well, for conservative vector fields, right now we kind of look at them and say, well, it looks like it could be conservative because this is the potential function, and we can kind of guess and check and say, oh, look, it works. Okay? Now we are going to have a very sophisticated way of actually determining whether something is conservative or not, and if it is, actually finding out what the potential function is. Okay, so we have something called the conservative field test. So let's start with little f of xy, little g of xy. We're going to say that these are continuous and have continuous first partial derivatives in some open set D. And we say f of xy, which is little f, little g, is conservative No, I don't like the way this is sounding. Let me add a word. If period, remove this and, I don't like the way I have it worded. So if we have f and g are continuous and they have continuous first partials in some open set D, we know that f of xy is conservative means exactly the same thing as partial f partial y equaling partial g partial x at each point in D. Sorry about that. Okay. So in other words, I mean this is the big part. I kind of messed up the condition, but the condition is obviously that you have to have continuous functions that make up the vector field, and their partial derivatives have to be continuous. Now, as far as determining whether a vector field is conservative, for us, all we have to do is check whether partial f partial y, in other words, partial y of the first component is going to equal partial x of the second component. If that is true, then we know that it's conservative and it's that easy. Okay? So, for example, show that the vector field f of xy, there's just so many f's. Which is equal to 2xy cubed for the x component and 1 plus 3x squared y squared for the y. Show that this is conservative. Catherine, what are you doing over there? Okay, if we saw this problem in 15.1, you'd have to actually find a potential function and say, look, if I take the gradient of this potential function, I get this as the potential vector field and life is good. Now, all we say is, well, let's figure out partial f partial y. What's partial y for the f function? What's partial g partial x? Done. That's all you need to do. That's it. Okay? I'm sure. Now, obviously there's going to be more, but as far as determining whether something is conservative or not, this is all you need to do at this point. It is partial g partial x. Right. And then all the stuff we just talked about you couldn't do. The fundamental line theorem of integrals can't do it because it's not a conservative vector field. The whole thing about starting at one point and ending at the same exact point, work being 0, can't do that because it's not conservative. So all these conditions that we've been talking, or all these cool things we've been talking about, this condition needs to be met. Okay? Now, let's actually find a potential function. So continue the last example. Find the potential function for the vector field 2xy cubed 1 plus 3x squared y squared. Okay. So there's really two ways to do this. Okay? Two ways to do this. One, we find the derivative of partial phi partial x dx. I'm sorry, did I just say rough morning today. Find the integral. Sometimes my head is already ahead of what I'm writing. So what I meant to say was integral, but I was already thinking about the derivative in the integral. Okay. Let's just pretend that didn't happen. So, we're going to find the integral of partial phi partial x with respect to x. That's what we're trying to do. So in this function, this vector field, which of these two has to be partial phi partial x? The first one, because in order for this to be the gradient of phi, we would have calculated partial phi partial x, and this would have been it right here, right? So what that means is that we're going to calculate the integral of 2xy cubed with respect to x. Well, that's easy. X squared y cubed plus some constant. I'm going to call it k because it's a different constant. It could be a function of y. This is the difference between what you're used to and right, because you could have a y term in here that when you took the partial derivative of with respect to x ended up going away and you don't see that. Does that make sense? So it's very important that you understand that, yeah, there's a constant, but it could very well have a y or be a function of y. Okay, so now what we're going to call this is that this has to be equal to phi. Okay, so loosely stated, this is the potential function. What we're going to do now is kind of cross-check it and see what happens if I do partial phi partial y. Well, partial phi partial y has to be 1 plus 3x squared y squared, right? According to this function here, if I take the partial derivative with respect to y, what do I get?
Wait, one more time.
So if this is phi currently, I'm not done with it, but let's say this is what our potential function is. What's partial phi partial y going to be for this function? 3x squared y squared plus the derivative with respect to y here. Okay, yes, and that's now what I mean by kind of double checking your potential function here. Clearly we have that 3x squared y squared that we need to have here, which is good. The only thing that's off is that we need this 1, right? So that since partial phi partial y equals 3x squared y squared plus 1, and I'll make the connection here, right? This means that k prime of y has to equal 1. Yes.
Why didn't you do the integral of partial phi partial y?
That's option 2. Gets you to the same exact answer. So k prime of y equals 1. How do I find k of y? Integrate. So now we get, and I guess I should say I'm integrating with respect to y here, right? So we get k of y equals plus maybe, well, no, at this point we rule out the function of x because we already took care of partial phi partial x. This could very well be just any constant now. Okay? So, the potential function phi of xy is going to equal, we have x squared plus y cubed plus, we figured out k of y had to be y plus maybe some other constant.
Why do you use K instead of C?
Well, I used k because initially it's going to represent maybe a function in terms of a variable, and usually when people see c, they think number. So I guess we probably could use a c here, but anyway. Here's the potential function. Okay? We good so far? Well, pretty much. Now we're going to actually put it all together with one cumulative example. So we kind of done baby steps. We've said, oh, here's a vector field. Let's show it's conservative. Okay, now let's find the potential function, right? What are we building up to? Actually calculating the work or the line integral from one point to another for a conservative vector field.
Are we not going to do the second option yet?
We don't, I mean, it's, oh. Option 2. Use partial phi partial y to start. ... It's the same exact procedure, except when you integrate, it'll be a constant in terms of maybe x, and then you have to cross-check it and take partial phi partial x and see what's going on. Same idea. Yes?
What if you do like the integral of partial phi partial x, and then you set that equal to the integral of partial phi partial y, and you like solve on?
Well, if you set them equal to each other, that I mean, you can't because they're not.
The integral.
The integral of those. Well, they may not necessarily be equal to each other. That's the problem.
Well, if you take into account like the k in terms of y, and then in the other one it's just be a constant because you already knew that. Maybe I'll just show you what I have.
Okay. Yes, show me. Yes.
Wasn't like what we did before, just to take the integral of the x component plus the integral of the y component, but like one term.
What do you mean when? Did before? What do you mean before?
Like before when you first mentioned potential functions.
Potential functions? When we first mentioned potential functions, we said that a vector field was the gradient of the potential function.
Right, so
And that's how we knew the vector field was conservative. So we found partial phi partial x, that was the x component. We found partial phi partial y, and that was the y component of the vector field.
oh, so you can't just take the integral to go the other way around.
Right. So you take one component, treat it with respect to x, and that'll give you what the potential function looks like. The only thing that's off is that maybe we don't know the function in terms of y that's attached to that, which is why you set that equal to partial phi partial y, and then you can go from there. Or take partial phi partial y, integrate, you get a function in terms of y, and then maybe you just don't know the x part. See what I'm saying?
Will one be easier than the other sometimes?
Not, I mean, really, they're both pretty straightforward. Okay, so last example. Find work done by the vector field let's call it f of x y equal to y cubed plus 1 for the I component plus 3xy squared plus 1 for the j component. In moving a particle from 0, 0 to 2, 0 along the semicircle shown here. Okay? So now we're kind of building an arsenal, kind of. We could parameterize the curve or do things we did in 15.152, but first thing that you should check, because life is easy when things are conservative, I hope you've seen that, we want to check to see whether or not f is conservative. Okay, because if it is, then we don't have that much work to do. Okay, so how do I check if f is conservative? Partial f, partial y. It's always opposite, right?
Okay.
What's partial f, partial y going to be?
3y squared.
3y squared. And let's just confirm, does that equal, if I look at g, partial x?
It does actually.
How nice. So then all we need is the potential function. Okay, so I don't care what path this is. If I know the potential function, then I just plug in endpoint 2, 0, starting point 0, 0, subtract. We're done. Okay? So, just for Eddie, since we know partial f, partial y, since we have that partial phi, partial y is what? 3xy squared plus 1. then if I integrate that with respect to y, then I get that, bless you,
Plus 2.
phi of xy is going to be what?
Plus y. Plus 2.
Xy cubed plus y plus some constant, maybe in terms of x, right? So then now what do we do to finalize our potential function? We do partial phi, partial x. Partial phi, partial x will be y cubed plus 1 plus possibly...
Wait, was it just be y?
Oh, there's nothing there. My bad. Still stuck in y mode. So y cubed plus 0 plus k prime of x. So now what does this mean? So k prime of x has to match, it's up here, 1.
Wait,
So-
which one's up?
Yes.
How did you get just y to the third?
Because the derivative of x is 1. Y cubed is just a constant.
I see.
Chapter 13 is now in effect, right? All the chapters we've done coming into play. So k prime of x equals 1. So if we integrate k prime of x dx and integrate 1 dx, what do we get for k of x? X plus some other constant. So the potential function that we're looking for, make sure you go back to the first one. We have xy cubed plus y plus x plus maybe this other constant. Now, the nice thing about this, so if I ask you to find the potential function, this needs to be there. But when we're actually evaluating the line integral, you guys understand that this will go away, right? Okay. So, work, which is f dot dr, is simply going to be now phi of, what was our endpoint? 2, 0, minus phi of 0, 0. When you plug in 2, 0, x is 2, that's 0, that's 0. You get 2 minus, everything is 0. So 2. Okay? Now, I'm not going to do anything else, but I do want to point this out. Let's say you're in a bind on an exam and you totally forgot how to find the potential function, but you're really good at parameterizing curves or integrating along paths the old-fashioned way. Could you say, I'm going to just do this and go from here to here? Path independent, you can do whatever path you want. Okay, so either way you do it, you're going to get 2 as the answer. All right. 8 o'clock, we're good. We finished. Hooray. Tomorrow, Green's theorem.